Okay, this is a new problem. A baseball pitcher throws a ball at 160 kilometers per hour. Now, just in case you're wondering how fast that is, 160 kilometers per hour is basically 100 miles per hour, which is a real fastball in the Major League Baseball. If the ball starts from rest and the length of the arm swing is 2.25, so in other words, when the pitcher winds up, as you can see, I'm fantastic at art. If the pitcher winds up, then he pulls the ball out well behind his shoulder, and then he throws it, and he kind of steps forward, and the ball leaves his hand when his arm is outstretched. So that distance, I kind of estimated to be about just over 2 meters. What's the average force exerted by the pitcher on the ball? And the mass of the ball is 150. So, in order to do this problem, once again, we're going to go and use our impulse equation. Delta P equals F net delta T. And again, the applied force on the ball is the net force in this case. We can ignore gravity. It's not going to play a role. It's insignificant in comparison to the force exerted by the person's hand. So therefore, we can solve for F net. And we're going to do it like that. And once again, we can say, all right, well, that's just simply M delta V. The problem is that we don't have delta T. We have delta V because if we write this out, okay, well, we know that's 150 grams, that's 160, and that's 0, because right here the velocity is 0 meters per second, and over here the final velocity is 160 kilometers per second. Sorry, per hour. And so we can just divide this by delta T and we'll have our F net. Well, the problem is what is that? We don't have that. So we can't solve it yet. So this now becomes a kinematics problem. We have a few kinematics equations. We could try this one. And we also have this one. That's a plus. And we also have this one. However, if you'll notice, the only thing we really have here is the delta D and the VF and the VI. We don't have T and we don't have A. So the one we're forced to use is that one to figure out what A is. So if I solve for A from here, because I can't solve the other ones, that's the only one I can actually solve anything with. So using this one, I can say A is equal to VF squared minus VI squared all over 2 times delta D. Now that's going to be 160 divided by 3.6, converting to meters per second, squared minus, well, initial velocity 0 squared is just 0, divided by 2 times 2.25 meters. And my acceleration comes out to approximately 439 meters per second squared. That's a pretty big acceleration. Now, once I have that, now I know some of you would say, okay, well, at this point, if you have the acceleration, you have the mass, you can go ahead and multiply them and get your answer. It's true, but let's just stick to our initial solution here, although that will probably work, but it's I'm just going to follow my initial solution right now, which was to find T. So if we want to find T, we would go T equals, say from this equation here, we'd say T equals V final minus V initial all over A. And that is 160 over 3.6 minus 0 all over 439 meters per second squared, and that's going to give me, I believe, 0.1 seconds, approximately. Now that I have that, I can now put that value into there. So now I can, or well, more precisely, there. So now I can go, my F net equals 0.15 kilograms times 160 over 3.6 minus 0 divided by 0.1, and I believe the answer comes out approximately equal to about 66 newtons of force. Now, for those of you that said, well, you know, what about just going F net equals MA, since we have both M and A? And if we did that, obviously 0.15 enter 439 times, and that gives us 66 as well. Understand that the impulse equation and the second law are actually related. They're not distinct equations, because the impulse equation is derived from the second law. So there's our final answer. That's the average force that the pitcher's hand is pushing the ball for that 0.1 second that he pitches it. Thanks for watching. See you next time.